First of all, let's talk about area estimates in the energy norm. And to motivate this, I want to show you something pretty incredible to me when first time I saw this. Okay, so let's again solve. So let's take an example. Take an example. We still use the simplest function here, partial u partial x. Let me say plus sine of x, sine of pi x equal to 0 for x in the domain 0 to 1, and with u0 equal to u1 equal to 0. Okay, can somebody tell me what the solution is for this example?
Sine pi x over
Yeah, u exact should be equal to sine of pi x, and what's the constant here?
over pi x. Oh, pi squared.
Over pi square, exactly, because every time, so first time you take a derivative to sine, you get a cosine of pi x times pi. The second time you take a derivative, the cosine becomes minus of sine, and you get another pi out of this. So the pi square gets cancelled by taking twice the derivative, and the sine becomes minus of sine after taking two derivatives. So we should get a u that is tops at 1 over pi square, and it's a sine function. Okay? And let's try to use finite elements to solve this. And actually, let me code up a script. Let me call sine FEM for this. Okay. And so let's put an n equal to 5. Let's say 5 elements. And again, let's randomize the points. So x would be a rand of a minus 1, 1. So basically, I'm going to sort this. Okay, and x is equal to 0, x, 1. Okay, so let's evaluate this. X, I get a bunch of randomized x's. That's good. Okay. And let me define my h to be x2 to n minus x1 to n minus 1. So that's my intervals. And let's build our matrix A. The diagonal parts of the matrix A is 1 divided by h, 1 to minus n minus 1 plus 1. I think I need this divide. Element-wise divide h2 to n. Right, so that's our derivation of the diagonal part of the matrix, and the off-diagonal part of the matrix is a diag, and the off-diagonal of the matrix is 1 divided by h from 2 to n minus 1. I'll shift it by 1 to get diagonal on the upper side, and I also need to shift it by minus 1 to get the diagonal on the lower side. So let's run it again and take a look at the matrix. It's only 4 by 4. It's a very small matrix, and it looks like I think we have the right thing. All right, and also let's utilize our what we learned about Gauss quadrature, okay, to compute the right hand side. So my b is, let's first initialize at zeros, n minus 1 and 1. So that's the size of my b, my right hand side. And the right hand side is the integral of the basis function multiplied with the right hand side. And our right hand side is the sine function, right? Okay, so the basis functions are piecewise linear functions that goes from 0 to 1 and then back to 0. All right. So so I'm going to loop I goes from 1 to n minus 1, and I want to split the integration into two domains because my basis functions is not smooth, right? So and Gauss quadrature is good for smooth functions. So if I split it into two parts, then each part is going to be smooth, and I should get a good function to integrate. So part 1, my basis function is going to be, first of all, let's get the Gauss quadrature weights. Gauss quadrature weights of part 1. Gauss quadrature weights of part 1 is x Gauss, w Gauss is equal to LGWT. That's the function we used the last time. It's called Legendre Gauss quadrature. It's basically a Gauss quadrature for integrating an unweighted function. So integration of just a function. There are other Gauss quadrature ways that are better for integrating a weighted integral of a function, an integration of a particular weight times a given function. Okay, but for this, we are just going to use the regular quadrature. So let's use 10 points, which is usually good enough, right? 10 points and I need my x of I and xi plus 1. That's the two ends of my integration interval in part 1. And the function I want to integrate is going to be, it goes from 0 to 1 as my x goes from xi to xi plus 1. So it is xg, the location of the Gauss quadrature, minus xi divided by xi plus 1 minus xi. Right? This is my basis function, and I need to also multiply this by my right hand side, which is sine of xg times pi. Is that right? That's the value of the function at xg. I want to integrate. Is the basis function times the right hand side. Okay. So b of I is equal to sum of f times wg. That finished our Gauss quadrature. And then we go to our second part. Part 2. That's when the basis function goes from 1 back to 0. And then our quadrature interval is xi plus 1 to xi plus 2. Right? And also my function, instead of xg minus xi, I have xg minus xi plus 2 and xi plus 1 minus xi plus 2, because I want the function to be equal to 1 at xi plus 1 and 0 when x goes to xi plus 2. Right? And again, my bi now equal to bi plus this. Alright, any questions on how I constructed the right hand side? No? Then my u is equal to a backslash b. Right? Yes? Question?
In part 2, is it you're setting bi plus 1 or you're setting bi again?
I'm setting bi again because...
I see. You're adding the new part.
Yeah, the part 2 is actually over a different interval. Alternatively, I can do a different loop. I can loop over, instead of looping over the basis functions, I can loop over elements. In that way, I'm going to be setting bi and then bi plus 1 within each loop. That's right. Okay. So I have u, let me just take u is equal to 0 and plus 1, 1, because I want I want to include the boundaries. Okay, then u of 2 to n minus 1 is equal to a backslash b. Okay, so let's run this function. We get a solution u, right, that looks like it's going larger and then back to 0. Okay, now I did this not just to show you how to implement a finite element, because we have done that before. I want to take a look at how accurate the solution is with only 5 elements. So remember, the analytical solution is sine of pi times x divided by pi square, right? Let's take this minus my u. What do you think the error, the order of magnitude of the error is? Remember, we have a sine function. It's not a polynomial. It's not anything, right? Just give me an estimate with 5 points. Hmm? 10 to the minus 5? That's pretty accurate with 5 points, right? Any other estimates over there? Huh? Be bold. Okay. No more? Let me push my enter. Well, 10 to the minus 16. Weird, right? Are we just getting lucky? What if we just take 2? Just 2 elements, okay? And let's run it again and look at the error again. 10 to the minus 16. Okay, with this motivation, with this question in mind, let's take a look at the error estimate, and this is going to reveal to you why we are getting so little error. Okay. So the first thing I want to tell you is that the error we just saw, 10 to the minus 16, is actually not the error of finite elements. Because what we have just been doing with 2 elements, so x is 0, 0.1 and 1, so it's my x is 0, 0.1 and 1. If the analytical solution is like that, what I'm getting is almost exact solution here, but a linear function that comes over here, and then another linear function that goes over here. The error is actually huge, right? Because even though I'm getting the exact solution here, I have such a gap between the analytical solution and my finite element solution, right? Remember, the finite element is not finite difference. We are not just capturing the solution at the grid points. We are actually approximating the solution using a whole function. And this piecewise linear function is my approximation. It just happens to be almost exact at the grid point. And we are going to look at why. Okay? I will tell you why. The reason is that the finite element is optimal for a particular type of error. And that particular type of error is called the error in the energy norm. And in this case, the error in the energy norm for the Poisson's equation is the error in the gradients. In another way, the finite element solution is the optimal in minimizing the error between the gradient of the finite element solution and the gradient of the real solution. And if you think of how do you minimize the error of the gradient, minimizing the error of the gradient means I would take the average of the gradient of the real function and just to use the, because I'm restricted to piecewise linear functions, right? Minimizing the gradient, if I'm restricted to piecewise linear functions, I'm restricted to piecewise constant gradients. And minimizing the error of the gradient means I'm just going to take the average gradient and apply that to my piecewise linear function.